Greetings, everyone. My name is Ujjwal Vakre, and today I'll be presenting on the paper Accelerating Ecological Sciences from Above, Spatial Contrastive Learning for Remote Sensing. This work was a joint collaboration between Cornell University, a New York Natural Heritage Program, and New York Fish and Wildlife Department. So today I want to highlight a critical problem in ecological management, which is invasive species. These aren't just a nuisance. These are like non-native organisms causing estimated billions of dollars of economic and ecological impact annually. To combat their spread efficiently, we need precise strategies for deploying observers to key locations. The current obstacle to using cutting edge machine learning, especially neural nets, for this kind of environmental sustainability lies in data. These powerful AI tools thrive on massive label data sets, but for environmental applications and nonprofits, the effort required for ground truth labeling is often too expensive and laborious to scale, right? So this creates a bottleneck, preventing full utilization of these techniques and the like potential. But fortunately, I think there's a clear path forward. Remote sensing data is abundant and inexpensive to obtain. So the central aspect of this research was how can we harness this accessible satellite data images to create efficient invasive species management systems. So coming to the approach. So the approach of this paper tackles with this data scarcity challenge head on by basically utilizing unsupervised deep learning techniques for dimensionality reduction of remote sensing images. The core idea is that reduces sample complexity for downstream tasks and decreases the need for larger labeled data sets. Their specific technique is spatially augmented contrastive learning. Their hypothesis was that training neural nets to classify two nearby patches of landscape, such would induce meaningful and low dimensional embeddings. So as a result, this approach improves on like previous methods and naive classification problems for large scale data sets of invasive species observations. It also outperforms several baseline models in active learning simulations for both invasive species and also land cover classifications, as we'll see in the coming slides. So let's talk about the background motivation. So like this, the like over the years, neural nets have completely transformed, like the whole landscape, and so like they're used in say facial prediction and in natural language processing tasks like language translations and so these were basically exemplified by mainly two factors if you think about it. First is the availability of large data sets. Second is the availability of high power hardware such as GPUs and DPUs like the H100s, A100s, and so on and so forth. Remote sensing has also been benefited from such efficient data processing, and commercial satellites like the Econos have increased research interest in ecological applications of such technologies. So coming to the next point, so let's talk about how the invasive species management and data collection process was done. So let's let's delve deeper into this application. Like mentioned before, this was an ongoing collaboration with the New York Natural Heritage Program. So basically, this organization manages and coordinates invasive species data within the New York State using their program. I mean, we're using their program called the IMAP Invasives program. You can check out their website. invasive species are basically non-native organisms causing like great harm to the environment, economy, and also sometimes human health. So like the example, one of the examples that was highlighted in the paper was the um, the the hemlock woolly algae species, which basically feeds on the hemlock sap, disrupting their nutrient flow and ultimately killing those trees. So the NYNHP collected over 200,000 observations across the New York State over 30 years. So these data points, as you can see on the image, have been visualized. So like, but like collecting this sort of data is highly laborious and also like very cost intensive program because it requires a lot of professionals, volunteers, citizens, and scientists coming together, labeling all those species. So uh, given the limited resources that we have, efficient allocation of these resources to like high likelihood locations is like paramount. So uh, there lies our problem. Coming to the next slide. Uh, so the central problem is again when trying to automate, the prediction of invasive species locations from satellite images is sample complexity. Neural nets typically require large labeled data sets for many critical species. Like especially those they want to monitor before a large outbreak occurs. Observations are like very few, leading to a limited labeled examples. However, satellite imagery is easy to obtain with the advent of Google Maps or Apple Maps. So this basically suggests that we have like a powerful avenue at our disposal. That is, we have like unsupervised learning for a feature extraction and also abundant unlabeled satellite images. So this basically aims to overcome the bottleneck of scarce labeled data set. So now coming to the data set construction slide. So their data set is derived from the IE maps invasive programs, as I mentioned before. This focuses on like the 10 most observed invasive species in New York, such as the modernist chestnut, honeysuckle, Japanese knotweed, as you can see in the breakdown below, to basically ensure like spatially balanced data set and address observation correlations and density near cities. Observations were subsampled across 0.01 degree latitude and longitude grid, ensuring there's no neighboring observation overlap. So this yielded in a final data set of some 6,500 odd observations with 10 roughly balanced uh, species classes. I mean, it's like not extremely balanced, but this was the data set that was been worked with. And for each location, a 512 by 512 pixel RGB remote sensing image were obtained via Google Maps. So the key insight here is that while most invasive species are not directly visible from satellites, their preferred habitat types, for instance, the hemlock woolly algae prefers, hemlock trees around, found in, forest. These were observable, pretty observable from the satellites. So now coming to the core concept of the uh, paper here. So the concepts of embedding is pretty fundamental to this like approach and the like methodology. So embedding, what are embeddings? Embeddings basically represent data such as like words or images as like dense vectors in a low dimensional space, right? So in natural language processing, for example, word embeddings are generated such as the words in similar context, or neighbors, or like similar paragraphs have like similar vector representations. This is often achieved by optimizing a loss function based on a word and its neighbors. So they extended this idea to satellite images, and satellite images of like geographically nearby locations should or could basically exhibit similar embeddings. So yeah, so this was the core concept behind the methodology. Coming to the next slide. As you can see, so their like innovation is to spatially augment contrastive learning instead of directly optimizing embeddings via triplet loss, as we saw in the case of tile 2 vector. So they obtained them as a byproduct of classification tasks, extending contrastive learning to spatial domains by leveraging the neighborhood relationships of remote sensing images. So let's look at the diagram below to like understand this process. So like we have two remote sensing images here, X and N, and where N is a neighbor of X. Both images are fed into the same neural net, F, to generate a low dimensional embedding. So the network is trained to classify X and N as neighbors, right? So they achieve this by using a softmax cross entropy loss function, treating the inner product as the logic. So the specific loss function used here is given in the slide, as you can see. But here in practice, if you think about it, the computing the full denominator is pretty expensive computationally, if you think about it. So it is approximated by only considering negative examples from the same batch. Uh, so yeah, so this was the architecture. Coming to the next slide, we have implementation details and data augmentation techniques. So for their spatial contrastive learning method, the feature extractor is built on a ResNet 18 architecture model. Crucial detail here from more recent contrastive learning advancement is the addition of a small um, two two-layer MLP head, and so basically this MLP head like goes on top of a CNN model for training, and so this head consists of like 256 neurons, processes the CNN's output to generate embeddings, and then this MLP head is again after training it's discarded, and the features used for downstream tasks are taken directly from underlying ResNet's intermediate representations. So the model here was trained for 150 epochs with a batch size of 256, pretty a large model if you think about it, and a learning rate of zero point 0.1, and it was optimized using the Adam optimizer. Uh, Regarding data prep, the images were normalized to have zero mean and unit variance, like how we do data prep. So to generate like neighboring pairs for contrastive learning and triplets for tile 2 web, they extracted random 64 by 64 pixel patches from the original 512 by 512 images. Two such patches originating from the same base image constitute neighbors for tile 2 web and contrastive learning. To further augment the dataset and enhance robustness, they also apply various transformations random rotations, random flips, random zeroing of like 16 by 16 sub images. So like if you've taken CVIP, you probably know like all these terminologies, right? So coming to the next slide. Um, so yeah, so their first set of experiments evaluated the quality of embeddings generated by their unsupervised method for classification tasks. They compared their approach against several baselines, tile 2 vec, which uses a triplet loss, and autoencoder, and principal component analysis, and also like independent component uh, analysis. right? So for evaluation, the data set was split 70-30, like how we do. And 30% was again divided into 15 percentage, one for testing and one for evaluating. They assess the feature quality using two common classifiers, logistic regression and random forest classifier. And so the RFC was trained with 100 decision trees and with some impurity. Um, and the table basically on the side represents the average test accuracy and standard deviation for the invasive data set. As you can see, the contrastive method consistently, outperformed all the baselines for both the RFC and like other logistic regression classifier. This result is pretty significant, as it demonstrates effective feature extractions from unlabeled remote sensing images for a very difficult task where invasive species are not directly visible. So, yep. Going to the next slide. Here, critical application in ecological and biological domains is the ability to achieve high accuracy with like limited labeled data. So as ground truth labels are expensive to obtain, right? This led the researchers to investigate, their methods, performance compared to, fully supervised approaches. When varying the amount of available labeled data. So they compared their contrastive method against strong supervised deep learning baselines like dense net, ResNet, AlexNet, as well as the tile 2 features with an RFC classifier. And they simulated a real world scarcity by removing a variable percentage of labels from the training set, ranging from 6% to 75%, while unsupervised methods are trained on fully unlabeled data sets. So as you can see in the figure, so this demonstrates the results, the low labeled data regime graph and the full spectrum graph that show spatial contrastive learning consistently outperformed the classical supervised methods, especially in low labeled data regime, right? This basically implies that their method can significantly reduce the number of labeled examples uh, required to achieve like high accuracy, leading to substantial, cost saving and also manual work. So yeah, coming to the next slide. So here the ultimate goal of their collaboration with the New York Natural Heritage Program was to use machine learning predictions to intelligently, direct ecologists and scientists to locations likely to contain invasive species. To simulate this crucial, field deployment, they conducted active learning experiments on their invasive species dataset. So the the new aspect of this active learning uh, uh, is performed only on labels after unsupervised pre-training on all images. So this is like highly practical in the domain, like as remote sensing data is pretty cheap and inexpensive to acquire. I mean, like next to zero. It costs nothing to acquire, Google images, Google Maps images, right? Uh, so but the field work observations are pretty costly because you have to like send a lot of people to various locations, label those data sets, label those invasive species, and then get that data. So the premise here is that useful features can be extracted unsupervisedly, allowing them to strategically acquire the most informative labels. So as you can see in the graph, they initialized with the 256 labels first, and in subsequent rounds, 256 new labels were selected based on entropy sampling from predictions on unlabeled images. So they compared their contrastive model to a tile to vec, both, I mean, uh, and a standard active learning approach using, a resonant 18 model. So their contrastive method time and again like outperform the traditional active learning and tile to vec model. So basically, this demonstrated its potential for guiding label acquisitions in like large scale ecological surveys. So yeah, so coming to the next point. So like to gain a deeper understanding of the learned feature spaces, they performed a qualitative analysis using the TSNE method, like a dimensionality reduction technique for visualizing high dimensional data. So the TSNE visualizations show that the contrastive learning and tile to vec yield clear clustering for invasive species classes compared to PSA, and the autoencoder. So their reason that the L2 loss used in the tile 2 vec might lead to looser clusters. So potentially stopping generalizations, which could explain their methods better performance when compared to the other methods. Beyond the invasive species, they also demonstrated the generality of their method on additional remote sensing datasets for land cover classification problems as well. So they tested their method on the Eurosat. Eurosat is basically has 27,000 satellite images of various, various land cover types from Europe. And also, they tested their method on the NAIP dataset, which includes a fourth spectral band, uh, highlighting the method's ability to handle, multispectral remote sensing data as well. So this data set also, presents a challenge by having train and test sets from different geographical locations. And which basically requires a model to be extremely robust and also deal with, distributional shifts. So yeah, all in all, their method outperformed all the baselines across different data sets and had like cross functionality. Coming to the next slide. So what were the practical challenges and future directions of this paper? So while the results are like pretty promising, it's crucial to acknowledge the practical challenges and opportunities which come naturally with deploying such models. Firstly, it is important to know that even like a minimal accuracy of around say 25% can significantly assist fieldwork and complement classical approaches. So think about it. Like say if a model is 25% accurate, you don't need 25% of manual labor uh, if you can directly correlate. Again, so the problem's inherent difficulty lies in the fact that models predict suitable habitat, not direct species presence, as species are not often visible from satellite. So there's also habitat uniformity variations within seemingly similar habitats, such as like tree density spread and like pretty hard to capture. And also land cover granularity can also be an issue, as say coarse land cover types uh, like full thick forest may not capture specific tree species, a composition of specific tree species. And then also infrastructure impact, like proximity roads, trails, water bodies, highways, affect the spread, and it's like easily detectable from satellites, but not always captured by land cover data. So misclassification is also a concern, as similar habitats for different terrestrial or aquatic plants can lead to incorrect predictions, impacting management cost and also the effectiveness of the whole program. And also, secondly, data collection bias exists, right? Obviously. So citizens science data collections, like for example, often uh, introduce a roadside bias where like more accessible locations are monitored more frequently. However, for human mediated invasive species spread, this bias towards populated area might actually be beneficial. uh, in some cases not, uh, because it may lead to oversampling. uh, so yeah, and finally, key area for future work involves further studying of how seamlessly to integrate like these advanced machine learning methods into real world deployment for not just invasive species management but for other use cases as well. So let's talk about the impact. So all in all, this work made like several key contributions. They introduced a new data set of remote sensing images for invasive species management based on ground observations. Yeah. They also presented spatially augmented contrastive learning as an effective method for obtaining low dimensional embeddings from remote sensing data. Their experiments also demonstrated consistent outperformance against baseline models across three different data sets, their own data set, Eurosat, and NAIP. They showed how active learning in this embedding space can improve sampling complexity, simulating efficient field deployment. Right. So, like this work ultimately aims to accelerate invasive species management and then contributing to computational sustainability and in the broader sense monitoring of natural resources and environment in general. So yeah, so that's it from my side. Thank you, and I'm willing to take any question and answers for questions in the Piazza post.